Okay, lesson 1 from 6A, antiderivatives. Find my highlighter here. Okay, scroll on down here. And we're going to start today by mapping out a function and its derivatives. We want to think of differentiation as a process, with the question ultimately being, is it a process that we can reverse? And right now, I want you to look at just the red section of my little diagram here. So just the red section. Imagine starting with some function f of x. We already know we can apply a process called differentiation to get a new result called f prime, which happens to be a rate of change of f. But I can apply that process a second time in some cases, getting to a second derivative, and perhaps I can even go beyond that. So we've got this chain of derivatives, f prime, f double prime, and so on. What we want to consider today, what is the reverse of that process? And for now, let's just call it anti-differentiation, as in the opposite of a derivative. So in theory now, there's some new process where I could start with f double prime, anti-differentiate, and somehow get back to f single prime. And then perhaps I apply that process a second time, anti-differentiate, to get back to f. And maybe, just maybe, we started with f, but perhaps f itself is something you could anti-differentiate to get to something else entirely. Here I'm calling it capital F of x. If that were the case, then it would make sense that this capital F of x could in turn be differentiated to get back to little f and add to the chain, so on and so on and so on. Excuse me, I had to close the door there. Okay, so that's where we start. We're going to set up a definition here. We'll say a function, you could call it capital F for now. A function is the antiderivative of little f on some interval if it remains true that capital F prime is little f. I'm talking about this portion of my chart right here for all values of x. Okay, we don't know yet what this antiderivative is able to really tell us, but this is what the process would be. And you could, if you want, maybe think about finding antiderivatives for basic functions. Again, we don't know what it helps us with yet, but it's something we could try to do. For example, we could imagine a little f of x called 2x, and then try to find a capital F. Can we think of some function whose derivative would be 2x? And of course, the first thing that pops into our heads is x squared, right? The derivative of x squared is 2x. So maybe, just maybe, capital F was x squared. Okay, so that means we can take our 2x, anti-differentiate it, and somehow get back to x squared. But is that the only possible answer? Okay. Wouldn't it also be true if capital F was x squared plus 1 or x squared minus 4? Well, now we have a few different functions, all of which their derivative would be 2x, which that's maybe a reason for concern, and we'll talk about that later on. Okay, it's a whole family of functions. In fact, I could put any constant I want after x squared and result in a derivative of 2x. If little f equals x, is there a function whose derivative is x? Well, here's an example. And what I've done this time is I've put a plus c at the end, basically communicating we want 1/2 x squared, but you could add any constant you like for your capital F. Similarly, for cosine, here's a function whose derivative, or really a family of functions whose derivative is cosine. And we can do this for a variety of functions. But we're actually not super interested yet in learning all these different rules. Okay, so let's wait on that until a later date. Couple notes, capital F is not a universally recognized notation for an antiderivative, so we should not be using capital Fs on an AP prompt without explaining what it is and expecting a grader to know what you're talking about, okay? As we saw just above, functions that differ by a constant have the same derivative. And again, as I mentioned a moment ago, we could learn shortcuts for this, but it's more important to first figure out what an antiderivative actually tells you, okay? So let's start getting into that part of the story as we scroll. We already know that a derivative is a rate of change at a point on f of x. It tells you the slope in the graph. What exactly does an antiderivative, how does that show up in a graph? That's what we're going to investigate here. And for this investigation, I've put in bold some given information. Let's assume there is a capital F of x. You could even call it y equals capital F of x, such that the derivative is little f. So this fits right into the antiderivative as we defined it a couple slides ago. In fact, there's two different ways you could communicate this information in words. You could say little f is the derivative of big F, or alternatively, big F is the antiderivative of little f. So let's assume that's all established. We also want to recall from Calc A that, well, dy dx obviously is a rate of change of y with respect to x, but the dy and dx separated also have a meaning. And when we separate these out, they no longer communicate rates, they communicate actual amounts of change in y and x respectively. So with that all established, pause the video if you like to give yourself a sketch like mine here for your notes. But what I'm doing is I'm sketching not the capital F, but the little f. I'm sketching the derivative of the big F. And just to make things simple for ourselves for now, I've chosen to assume that this dy dx is a constant, so I can graph it as just a horizontal line in green here. Okay. And what I want to point out with this now, we start considering the area below this graph within a given subinterval. This sort of ties into lesson 0 now. For whatever reason, there's two x values of interest, we'll call them xa and xb, such that if I were to shade in all the area between the x-axis and my curve, I happen to get a rectangle, okay? And the width of that rectangle is going to be equivalent to some amount of change in the x direction. However much x changes to take me from A to B, I could call that dx. And meanwhile, the height of this rectangle is constant, right? And it's always equal to whatever the actual value of dy dx is. So I can label that height as dy dx. And if I now try to calculate area the conventional way, it's got me doing a height times base. It's a dy dx times a dx. Those dx's cancel, leaving us with a dy. And then we glance back up above and remind ourselves dy is an amount of change in y. And y is originally defined as capital F. So be very careful here. We graphed little f, but the area is telling us about big F, the amount of change in big F. I'm going to uncover my tape here. Area under an interval in the graph of little f tells you the amount of change to expect in its antiderivative. Okay. So just to summarize, there's information about capital F embedded in the area under little f. This is our first taste of how an antiderivative might show up graphically. It shows up as areas. Couple notes. We're typically going to examine antiderivatives over intervals rather than at specific points. That's a little bit different than with derivatives. It turned out to be fairly easy for us to find a derivative at a single point, but for antiderivatives, we need to construct an area. So we need two bounds on the x-axis to find an area between. It's also not going to be as straightforward to find specific values of capital F. Instead, we found how much capital F changed. That doesn't tell us what it was to begin with or what it ends up at, just how much it's going to change. Okay. Now, if this is still feeling a little fuzzy, that's fine. We're going to go through this demonstration again, but try to put a little bit more context into it. So I'm scrolling down where we see a similar diagram, but this time let's consider slightly different functions. It's fairly common to notate the position of an object as a function s, well, in this case, s of t, position according to time. All right. As you know from previous coursework, if we take s prime, that will give us the rate of change of position, otherwise known as velocity, which we might also call v of t. The units would be now meters per second. So we could say v is the derivative of s, but we, as of today, can also now say s is the antiderivative of v. And for that reason, we can make a similar graph. I'm graphing the rate of change first. I'm graphing velocity. And again, to keep it simple, we'll go with the horizontal line. Perhaps I have two t values of interest, maybe a starting time and an ending time that I notate on a horizontal axis. And just as with the previous diagram, we can find the width of a rectangle by calling it dt, some change in time measured in seconds. And meanwhile, the height is some value in meters per second because it's corresponding to my velocity. If I try to now find the area of this rectangle, I'm multiplying some value in meters per second times a width in seconds. We can cancel seconds again, leaving us with meters. Okay. So my result, my area, is not a velocity anymore. It's an amount of actual change measured in meters. From time A to time B, how much did the position change? The amount of change in position is what we're finding when we calculate this area below a velocity graph. And there is a special word for amount of change in position that you've probably heard before. It's called displacement. The long story short, you find an area under velocity between two given times, you've just calculated the displacement of the object between those two times. We still don't necessarily know what the starting position was or what the ending position is. We just know how much the position has changed. All right, scrolling down. So informally, change in the antiderivative of a function is the area between the little f and the x-axis. That's what we've seen a couple times now. Change in the antiderivative, we often use the word accumulation. And the units of accumulation are the product of the units of x, the units of f of x. Antiderivatives, these accumulation, they're relevant when the original function is a rate of change, like a velocity. But it's not limited just to velocity. Maybe I have a function, little f, that measures cubic feet per second of drainage. Maybe it's fluid coming out of a pipe. If you find the area under that rate of change for a certain time interval, you can walk away knowing exactly how much liquid drained out of that pipe in that time interval. Burps per falafel, kind of a silly one. But if this is something you could graph and find the area under that graph, you would end up with an accumulation of the total number of actual burps that occurred for some interval. Okay. Now, if this is still a little fuzzy, that's understandable. I think we're ready to move on towards examples with actual numbers that makes the process a little more tangible for us. Let's check out the next page. I'm going to stick with this common example of, position, displacement, these kinds of things. In fact, I'm going to throw in another word, distance. Position, displacement, distance. These are three things that are very closely related to each other, but they're not exactly the same. So we want to keep it straight which is which. Position is where I'm actually located. Displacement is now a net accumulation. How much did my position change over a certain time interval? Okay. But we have to take into account direction. If I move 5 feet to the left and then 5 feet to the right, despite all that movement, my displacement would still be 0. Distance, on the other hand, is a total length traveled regardless of direction. If I move 5 feet left and then 5 feet right, that's a total distance of 10 traveled, despite having a displacement of 0. So we're going to see these words show up in our example. We've got a unicorn that lives on a number line. The unicorn has a velocity of 3 meters per second as time is bigger than 0. S here, let's assume, represents position. So the unicorn starts at 0 on the number line. And the first task is to graph the velocity. It's pretty common with this kind of work, is to graph a rate of change. And then find the velocity at t equals 2. Well, I've already got the graph graphed. Unsurprisingly, it's a horizontal line. The velocity when t equals 2 is 3 meters per second. That's going to be the velocity anywhere that I check on a constant velocity. But now let's find the displacement. This unicorn has moved 3 meters per second for a total of 2 seconds. On my graph, that's equivalent to looking just from 0 to 2 and imagine finding the area, which conveniently is still a rectangle with a base of 2 and a height of 3 meters per second. My width here was in seconds as well, so seconds cancels out. Your final answer is in just meters. That's how far we've moved. That's the accumulation of position is 6 meters more to the right. The actual position, okay, the reason I'm able to figure this out here is because we were given the original position. We started at 0. So if we started at 0 and after 2 seconds we moved 6 meters, initial position plus displacement, 0 plus 6 is 6 meters. Okay. So coincidentally here, displacement and position are the same value. I guess I shouldn't say coincidence, but in this case, they're the same. They won't necessarily always be the same. Velocity at t equals 7. This actually goes off the graph, but still going to be 3 meters per second. Displacement. Imagine a rectangle, 7 units wide. It's still going to be 3 units tall. It's the area under velocity, 7 times 3, 21 meters. The position still happens to match up because we started at 0, we moved 21 meters, now we're at 21 on the number line. Distance traveled also ends up at 21 because we haven't changed direction at all. My displacement and my distance happen to be the same. That's about the most basic of an example we can see. So let's take it up a notch here. Now we've got a Yeti on a number line. And the Yeti's velocity is a little bit more complicated than our unicorn. In addition to that, we're not going to start at 0. When time is 0, at the very beginning, we're at 4 on a number line. First task, graph the velocity, which I've already done over here. I've even went ahead and started considering areas between velocity and the x-axis, which we've got a triangle here on the left. And then at some point we cross below the x-axis. So if we're always looking for area between, here's how I'm shading. I get actually another triangle. It's what I might call a negative triangle, which does matter, as we'll see in a second here. Okay. But if I want to find the velocity at t equals 2, it's not always constant, but I can easily plug a 2 into my velocity. I could also see on the graph at 2, my velocity is about 2 meters per second. Displacement at the end of 2 seconds. Now we're considering an interval from time of 0 out to a time of 2. The area under my curve, but above the x-axis, or t-axis, I should say, is a trapezoid. Here's the formula for area of a trapezoid, which is going to come up for us. It's good to refresh. I end up with the result of 8, my units is meters, 8 meters of displacement. Position, I need to take my starting position. Consider now that we've displaced ourselves by 8 meters. So starting at 4 plus 8 gets me the position of 12 on the number line. Find the velocity at t equals 5. Here's 5, down, down, down. It looks like about -4. You can confirm that by plugging in. Displacement. This is where things get interesting. I need to consider from 0 as my time out to 5 as my time. We know that displacement is going to be areas between the curve and the horizontal axis. I've got a triangle, and then I've got another triangle. Here's the area of the first, area of the second, but notice now I'm subtracting. This is a little different than area in geometry, where, of course, all areas were positive. But if we dip below the horizontal axis, any shapes that we have down there, any shading, any area that we're trying to find registers as opposite, which makes sense because we know that at t equals 3, the velocity went negative, indicating a change in direction. So in a way, you can think of this area here not as an accumulation, but a decumulation. We're starting to lose some of the displacement we had already acquired as we move back towards where we started. So I'm taking my positive area minus my negative area, 9 minus 4. We actually only are 5 meters away from where we started. And of course, we started at 4. So my position after 5 seconds, 4 plus the 5, gets me the 9 meter mark on the number line. But displacement considers the change in direction. We have a negative quantity. Distance does not make those same accommodations. Distance considers all movement as positive. So I'm moving 9 meters to the right and then 4 to the left. I'm still going to go 9 plus 4. The discrepancy between E and G is that my minus sign remains a plus sign when it's a distance calculation. So the total distance traveled was 13 meters, even though we only end up 5 meters away from where we started. It's assuming we're Yetis. There's an "are we there Yeti" pun in here somewhere. Part H, could we find an equation in general to figure out what's going on with the position function? And the answer is yes, eventually that's where we're headed, but it's not what we're going to worry about right now. I'm hoping it's becoming clear why we are so interested in areas under curves. We saw that in lesson 0. Now in lesson 1, we're learning that these areas correspond to changes in an antiderivative. So let's summarize what we know on the next page. I'm starting with the summary of Calc A. If f of x is a quantity, df dx is derivative rate of change. It shows up in the graph as slopes of the original f. That was all Calc A stuff. And now that we've started Calc B, here's the story so far. Suppose our original function, the little f, is actually a rate of change as opposed to an amount. The Little f is a rate of change. There's another function, perhaps called big F, that is the antiderivative of little f. And we can learn about this antiderivative by looking at areas under the graph of little f. Changes in capital F are an accumulation of whatever quantity whose rate of change we were measuring. It's the area under the little f graph. Last page. This is, again, more of a recap. The most common context that we'll see early on is positions and velocities. It's not the only context, but it's quite common that we start with a graph of velocity. We can learn about change in position being the antiderivative of velocity. We can learn about the accumulation of position change or displacement by finding the areas that appear under the graph of v of t, or rather between the graph of v and the t-axis. And then I've got another common example described below that, but I'll leave that for you to read on your own. As always, if you have questions, email me, ask me in class. Thanks again for watching, and we'll see you next time.